Let us begin. Hello and good afternoon, everyone. Welcome to another session of the CODA webinar series all about decommissioning. My name is Rianne Gilbert and I'm the General Manager at CODA. And today I'm very excited to host this webinar with CODA Partner Claxton to discuss paving the way for heavy lift operations in offshore decommissioning. As we go through, every time, please pop your questions in the chat and we'll get to them at the end during our Q&A session. So I'd like to get right into it by introducing Craig Baxter from Claxton. And so Craig, over to you.
Thanks very much, Ryan, and good afternoon, folks, and good morning from here in sunny Scotland. So as Ryan says, I'm going to talk through what we've termed as paving the way for heavy lift. So this is where Claxton offer products and services around preparing offshore infrastructure, particularly platforms and jackets for heavy lift operations. So we're really looking at some of our internal developed cutting solutions and recovery systems for removing conductors and jackets. So purely for context, more than a sales pitch, really just if you didn't know who we were, we've been in and around the decom market for over 20 years. But before that, we kind of were born out of looking at wellhead maintenance. So that was kind of the first spark of what the Claxton brand started to develop, was sort of looking at, existing wellheads, maintaining wellheads. And then we kind of bled into risers beyond that. So we continue to have a huge fleet of risers that can work across decommissioning, across drilling, across intervention. And then we've been in around the decom market since it kind of first kicked off sort of 20 odd years ago. So Gulf of America, North Sea operations. And from there, kind of gradually sort of built up between sort of organic and inorganic growth. So bought up a few different parts of sort of ProServe we purchased, which is where I came into Claxton. And then we bought a part of Oceaneering that was the ex-NCA. So we've kind of grown that inorganically, but the organic growth has come from really developing product and services internally. So we really tend to be more of an engineering solutions focused company, but we've built up a huge suite of sort of infrastructure of cutting services and products. And just to touch on what we do in the region, so across APAC, so most of this work in the last couple of years has been offshore Thailand, some of it offshore New Zealand, and a few of these wells were cut offshore Australia. And previous to this, we've been very active out of our Singapore base and that across the whole APAC region. So today, this comes from the UK work breakdown structure, but I believe it's very similar, whatever region you're working in. So we're going to touch on some of the aspects that we look at within decommissioning. So today we're going to speak about wells, so particularly platform wells, because this is looking at heavy lift preparations. So looking at where we can support well operations in preparation for heavy lift, and then looking at how you would then perhaps look at a topside removal. So not particularly standard, the application I've put into the presentation today, but it gives you a flavour of where the kind of non-standard, off-the-shelf solutions approach us and say, right, here's maybe a standard diamond wire, for example, doesn't quite suit the cutting challenge. So we develop solutions for those kind of quirkier challenges. And then from topside removal, then move into looking at substructure removal. So for us, that's jacket cutting, whether it's sectioning or below mudline cutting, to allow the heavy lift to then move in and remove the jacket. So this is all work that can be done either on the platform itself for the wells or through a smaller vessel to support the topside and substructure removal prior to heavy lift, because obviously heavy lifts are quite expensive vessels and quite hard to get sometimes. And just to touch on what we also do, so we've recently been purchased into the AF group, which is a Norwegian floated group of companies. So within that group, we have a sister company called the AF Offshore Decom. So they have a huge, it's called a VATS, environmental terminal in Norway. So they'll take structures from typically from the North Sea or from the European sector, float them into vats, and then they'll do the full dismantling and recycling at that terminal. But they're also involved in some of the upfront project management preparation work around decommissioning of those structures prior to them floating into vats. And then obviously with our cutting solutions, we also do a fair bit of subsea infrastructure cleaning. So that's the stuff that doesn't typically touch on heavy lift, but we do a lot of that off vessels as well, but I haven't covered that today. So from the point of view of where we would typically get involved from a Claxton perspective, so looking at what our cutting and recovery solutions are, we would normally get involved in what we call phase 3 abandonment. So for us, phase 3 well abandonment is the reservoir is fully isolated, all producing zones are fully isolated. Phase 3 can be either setting an environmental plug or cutting and recovering the wellhead. In the case of obviously platform wells, it's cutting and recovering conductors and wellheads. So as I say, we don't typically do the reservoir isolation, but it's environmental plugs which are to lock in any fluids that may be in the wellbore between the P&A and the top of the wellhead, and then the severance, the wellhead, recovery of the wellhead and the conductors from the below mudline cut. So this is a variation on a tool that we use for vessel-based suspended well abandonment. So the SWAT tool for us is essentially a perf wash cement tool, but it's not for downhole activities, it's for environmental plugging. So that's very near to the surface of the seabed. So typically it's used if you have fluids in your annulus or in your well bore that once you sever the well, you don't want those released into the water column. You don't want to have to flush them out, because that'd be quite a large volume of fluids that you have to deal with, either take on board and clean up or take on board and take on shore. So this tool sets an environmental plug typically just below where you're going to sever the well for recovery. In the case of preparing infrastructure for heavy lift, what this option would do is to actually put a cement head onto the existing wellhead, and that would allow you to perform perf wash cement operations for an environmental plug near the severance point, but to do rigless. So rather than trying to do this on a rig, which is again a relatively expensive piece of kit, you could do the deep set P&A and then move across to other wells, or float the rig away, come in and do environmental plugging with a relatively inexpensive piece of equipment. And then you can do all the severance rigless as well. So this is an option to look at for environment plugging. And then one way that we work typically for rigless operations to get access to the well, so whether that's to set an environmental plug or to do the severance and recovery of the conductors. So obviously for a platform well, if you're going to go into the well, cut below mudline and then recover the wellhead, you're going to then pull all the conductor from the cut below mudline up to the wellhead. So you then have to pull that in sections, sever it, remove a section at a time. So it's quite a slow process. If you want to do that on a rig, it's an expensive asset to tie up just for this. So typically what we see is this is done, as we would say, offline. So a rigless option would be to look at what we call a lightweight recovery deck. So the bottom left one is one of those decks. So it's quite a small footprint. You can either manually move it across well slots, or you can build it on a skidding system, so you can actually skid it across well slots. It basically gives you access on the deck above the well to go in, connect onto the wellhead, and then you can get access to put your severance tool in through that wellhead, do the severance, and then you can use this recovery deck to recover the casings and the wellhead up through the deck. You can set a set of slips on them, so the middle option has got upper and lower slips, so you can actually use that as a jacking mechanism, so you're not relying on the crane to do the jacking. So again, it allows you to work even more offline, because you can jack it up off the wellhead lightweight recovery deck. So once you've got the amount that you're going to recover in each section jacked up, you can sever above the bottom set of slips, release the top set of slips, and then you pull that section out and lay it down. The one on the right-hand side is a full sort of recovery system that allows you to put BOPs in there if you ever need to do any intervention on the well. So it kind of goes from a very small light footprint on the left-hand side of the screen to like an intermediate option, then a full system that has BOPs. It's got upper and lower slips. We integrate electric drill pin and cut into this system, so you can, once you start to pull the casings, you can automate the full system for the drill pin and cut to remove each 40-foot section. So you pull a 40-foot section, you drill through it, you pin it, you cut that section above the pin, you can lay that down, then use the pin to pull the next section up. So it's quite a large footprint because of the scale of the system. So it really suits, we've used this typically in the Norwegian sector where the platforms are quite large. So it really suits that type of application. Smaller platforms suit either the left hand or the middle option. So once you've got access to the well through a lightweight recovery deck or the full well raiser system, you're going to want to go in there and cut the well below mudline. So typically anything between sort of 10 feet and beyond, depending on what region you're in. So we typically start at that 10 feet, 3 meter kind of line. We would allow a little bit lower, so if we ever have to do a recut, we can come up a little bit and still meet the regulations. So for us, this is using Excalibur cutting solutions. So Excalibur is essentially an abrasive water jet cutting solution. In this case, applied to well severance. The same Excalibur is then, you'll see in future slides, you'll see it's then applied to the actual jacket pile cutting as well. So it's the same system, depending on what type of cutting manipulator you use is what the application is for. So in the case of Excalibur cutting solutions, a lot of the work, so when we look at the different aspects of what has brought Claxton together, so we had like legacy part of ProServe, legacy part of Oceaneering, and we had an existing part of Claxton. So a lot of the Claxton operations had dealt with platform wells in the southern sector of the North Sea here in the UK. Typically in the ProServe days, we were working off vessels, so doing a lot of subsea wells. And then the ex-Oceaneering and NCA equipment, they covered both platform and subsea, but predominantly subsea. So it was quite a good sort of marriage of experience of platform well cutting, subsea well cutting, and kind of pushing the boundaries of each. So bringing that together into the Excalibur cutting solutions gives us the benefit of knowledge of companies that used to be competitors now sort of fighting the same sort of fight together, and kind of bringing all that sort of 30 years of knowledge to the fore to develop a solution for whatever your cutting application is. So in the case of well severance, what we typically do is we go in with either a mechanical seal or a packer tool to allow us to set that in the well. What that does is it allows us to dewater below the packer. So we're essentially cutting in an air environment. So we obviously with high pressure water jet, and if you try to cut in a water column, the water sort of fights back against your high pressure water jet. So for us, the ideal solution is to cut in an air environment. And as you break through the different annulus, the air fills each of those annuli, and it just makes it easier to penetrate out to the outer conductor. So you're basically putting one tool into the inner bore to cut all the way out through to the outer, the low pressure conductor. And I think where we've sort of really looked at pushing the boundaries of what's capable for our systems is some of the examples in the right hand side. So really looking at the wells that have really faced or kind of presented real challenges regarding, you know, if you take the top one, for example, that's a 3-inch outer conductor. So maintaining the jetting pressure to get out through that conductor is quite a challenge. So for us, especially in that case there, because you can see there's no cement, so quite often the wells are presented to us as fully cemented, but you can see obviously in the top image and the right hand image, there's not very much cement or any cement at all in there. So they again gives you a slightly more challenging environment than a perfectly cemented well, because it's more difficult to maintain your dewatered environment in those wells. You can see in the bottom right well that it's got centralizers right at the cut line. So again, in that case, we're not presented with that well with those centralizers. We're presented with the casing sizes. So we go in and predict against the casing sizes. Then when we pull the well, we can see there's those centralizers in the well. So there's some of those things you only find out once you're in the well and you've cut and recovered it. In the case of the middle image on the right, you can see, so that's what's called a triple bore well. So it's actually got 3 producing liners within the well bore. So in the case of that well, for us, we go into one of those bores and we cut the whole lot out in one go. So these are applications that would be particularly tricky for whether you want to use explosives or you want to use a set of knives. You're not going to be able to do that type of well with that type of technology. So this abrasive water jet cutting really suits those more challenging applications. And then same with the bottom one, you can see it's a fully eccentric. So the inner casings are pushed all the way over to one side. So you can imagine trying to cut that with a set of knives. You're going to cut the 6 o'clock position very easily, but you're never going to reach out to the outer, the 12 o'clock position. Same with explosives. To be able to get that penetration out of the 12 o'clock position for that type of well is going to be very challenging. So again, abrasive water jet cutting, we wouldn't have known that that was so eccentric at that time, but we would have been able to see how slowly we were cutting out the outer conductor at that 12 o'clock position. So as I say, these are kind of some of the things that where we've taken on well challenges that have really pushed the boundaries of what we've been able to do, and we've learned along the way over the last 30 years of what is within the capabilities of the system. And then more recently, we've been pushing the kind of water depth limits of the system. So there historically was, we were a bit more conservative about the water depth capabilities, but some of the learnings from bringing other companies into Claxton branding, we learned that they already had sort of overcome some of those challenges, and then we pushed them again further in the last couple of years. So you've got an environmental plug in the well, you've severed the well, then you obviously need to, as I say, from the cut below mudline, you need to remove all of that casings. So you're going to have a lightweight recovery deck or a recovery system on top of the wellhead or above the wellhead to pull those casings. So you wouldn't typically use a rig for that because it's quite expensive. So you can see on the left-hand image, that's a modification of what we had previously used as a riser clamping system. So if you're running a riser, you typically are pulling tension on the riser. So that's a tension ring from a riser system that we've then modified to go on to what we would call a proven string. So the proven string that's sticking up through the clamp there on the left-hand image, that's actually attached to the wellhead on the deck below. So our cutting tool will be down inside the proven string all the way down through the conductors below mudline. When we're doing the cut below mudline, we're actually then we're putting hydraulic pressure below that clamp. And what we're doing is we're then pulling a bit of tension on the whole conductor string, so that once you've done the severance, you know that you've cut because the whole thing shifts up 6 inches. So it's really straightforward to prove a cut on a platform well, because you can physically show that, yeah, it's actually all shifted. So you know you've cut fully out to the outer conductor. The middle image is the one I mentioned earlier, which is the electric drill, pin and cut machine. So historically, we've used a mechanical system for this. So you may be familiar with what we call double drill units. It's basically a clamp that goes round the conductor. So you can imagine in the case of the middle image, you're cutting through multi-string conductors in one go. So in order to lift each 40-foot section of those, you typically put a lifting pin, which is what you can see in the top right image. So what you need to do there is obviously drill through those multi-string conductors. So if you imagine they're not cemented, what can happen is the inner conductors can be rattling around in there. So it can be quite a challenge to drill through. When you're doing it manually, you typically are a bit more conservative because you can you've got a feel for, okay, I'm going through one conductor, I'm hitting the next conductor. So you tend to be a bit more conservative so it can slow down the operation. And then we would typically in the manual operation do the double drill from either side, then put a pin through. Then we perform the cut above the pin. So what you're doing there is you're cutting the section above the pin, so you can remove that previous section, then you would lift the next section on the pin. So drill pin, cut above the pin, remove. So with this system, what we developed is a fully electronic, so an intuitive essentially. So as it's drilling through, as it meets no resistance, it advances a little bit quicker. So whether it's hitting cement and it's cutting easier than it is cutting steel, or it's cutting in an open air annulus, it moves a bit quicker. And once we're 50% through with the drill unit, it starts to cut above the pin. So essentially your drill piece is your pin. So you know when you're 50% through, you've got structural integrity. So then it starts to advance the band, in our case, a bandsaw cutting solution above the pin. So the whole operation just speeds up compared to doing it manually, relying on operators, not going too fast, not going too slow, doing the drill and pins separate to the cutting. So just the fully automated system gives you a lot quicker an operation than it would be to do it manually. So this is a system we have used in the North Sea. It can be either fitted into that large skid, which we call a well raiser, or it can be operated alone. It's basically on a small skidding system, so it can kind of come in and out with the conductor as you pull sections. So it would come in, do the drill pin, do the cut, take that away, it would skid out till the next section was lifted. And then a relatively straightforward, but a really, simple and effective way of laying down conductors, because that's always the challenge. You've got a 40-foot section of multi-string conductor, then you've got to try and rest it down on whether it's a barge or on a vessel, to then be able to lay it out to the side to then go back and pick up the next 40-foot conductor. I have to say the image on the left is not ours, that's Hiramaz. That's their conductor laydown system where they rack, I think it's 12 sections of conductor. So that's a really good system because it allows them to cut more in one operation. So a typical operation would be a 40-foot section. They cut a larger section, so it speeds up your whole operation because you're doing less cuts per conductor pull. And then they can stack them all and lay the whole lot down in one go. And then they pull the cartridge out and move that to the side. In the case of our lay down buckets, we just do a section at a time. So what that does is it lays down a section. It allows the crane to go and stack those sections while our system's still working on the next 40-foot section to do the drill, pin and cut. But it does mean that you can work slightly offline of the crane as well as the rig doing this. So you've taken care of the wells, you've got your environmental plug in there, you have severed the well, proved the cut, and then just pulled all those length of conductor from the below mudline cut up to the wellhead. So you've essentially taken all the steel work out of the well that you need to leave a clean seabed. So the next step for us would be that with the topsides all prepared, as in all the hydrocarbons have been removed, all the systems have been flushed and disconnected, and then we would look at how we sever the topsides. So typically the heavy lift would come and pick up the topsides and then remove that and then come back for the jacket afterwards. So we would offer solutions to look at cutting the topside from the jacket so a heavy lift can come in, remove that, and then sail away. So again, looking to do this off a smaller vessel, so not looking to use a heavy lift at the point of doing the cutting operation. And we do offer some of the more standard sort of diamond wire saw applications. There's different methods of doing leg cutting. You can, in many cases, they just gas axe it because they've got good access to the legs below the top side. It's an application where there wasn't good access. It doesn't really suit a standard diamond wire because the base of the top side is solid, so you can't actually get down below to cut the legs below the top sides. So in that case, you're going down actually inside the leg to try and develop some kind of cutting solution. So for us, this kind of comes as a, okay, whenever we thought about this when we were putting this in, but this is quite a challenge to cut these legs to remove the top sides. In this case, the legs are still in the seabed because they've got derogation at the moment to leave them until they decide where about within the leg or at concrete base they may have to remove them in the future, but the legs are still there as far as I understand. So this is removable of top sides to allow them to take that away and dismantle. So this is a 10-meter leg. It's steel and 850 millimeters of concrete, then steel. So 2 lines of steel with cement in between. So for us, we started with a blank sheet of paper, looked at different options. So unless you're familiar with a pull saw, I'll explain. So a pull saw, typically a diamond wire clamps onto what it's trying to cut and it pushes the wire through the cut. So as the wire is rotating on the saw, it starts to advance through. So that's what we would typically call a push saw. A pull saw, in this instance, you wrap the wire around what you're trying to cut, and as the wire's rotating within the unit, you start to pull the wire through what you're trying to cut. So it's a standard operation for large-scale demolition. They use it in quarrying as well for cutting up sort of granite slabs and the likes. They use it for wreck recovery. It's similar to what you would do with a chain cutting solution, the way that they manipulate chains to cut large wrecks. So for us, we thought, okay, we've got some of these units. How could we fit this to the application? So we looked at boring holes. So you can see in the bottom left image above the text there, we essentially drilled locations round the legs. So the top middle image, you can see that's us bored through the steel, the concrete and the steel. Then we fed the wire through from one hole round the outside with a rope access tech into the next hole, and then we fed it back into the actual pull saw unit. Pull saw unit does the rotating of the wire and it does the pulling of the wire through. So we basically just went round and cut section by section within between those hole cuts. And then we're going to leave the top sides on. So again, all done off a smaller vessel or from the actual platform itself. So they're going to leave it over winter. So they just put what they call shear keys into those holes. So they've done the severance, they put the shear keys in so that nothing could move. And then they came back with a heavy lift vessel afterwards. And I've not really covered the basic stuff of, yeah, we can do diamond wire saws or, abrasive cutting solutions for topside severance, because they're pretty standard. It was really just to highlight some of the more quirky applications where maybe a standard solution doesn't quite fit. So that's kind of where we would see that we would really relish the challenge of, okay, this has never been done before. Excuse me. How do we sit down with a blank sheet of paper and work with a client as to what are the options for performing those cuts? So you've got your wells dealt with, you've got your top sides floated away on heavy lift to your onshore dismantling, and then the next step would be to remove the jacket. So in the case of jacket recovery, so a lot of the jackets out there have been placed on the seabed, and then you can see in the left-hand bottom image, they've actually pinned through the jacket. So that's a really large pile that's been hammered in through the jacket leg all the way down below mudline into the seabed. So as they do that, what happens is the soil within the pile starts to migrate up, because obviously you're displacing the soil somewhere. So you'll compact a fair amount of it, but it starts to migrate up within the pile. So it's actually higher, can be higher within the pile than it is outside the pile. So for us to then go and prepare the jacket for heavy lift removal, we need to go into that pile, cut below mudline. So whether it's, in the case of the left-hand image, it's a pile that's pinned, we call it pin pile through the jacket into the seabed, or the middle image, you can see that one's actually got skirt piles as well. So those are the small piles with the brown pile locating sort of cone on top of them. So those skirt piles are shorter piles, but they're still piled into the seabed round about the jacket legs. So in that case, you've got a pin pile to cut on the jacket and you've got these skirt piles to cut. So in order to get into cut location 3 meters below mudline, you've obviously then got to go in the pile and remove that soil from within the pile and expel it out with the pile. And that allows you to then go put a cutting tool below mudline, perform your cut. So the skirt piles are relatively easy because you've got a short distance from pile top to below mudline. It could be in the case of sort of 10 to 20 meters. So it's relatively easy to get a soil plugs removal tool in there. Typically what we use for that application is an airlift tool. So you essentially, so if you imagine the bottom of the tool, we inject air a couple of meters above the bottom of the tool. So that creates a vacuum at the bottom of the tool, and it essentially sucks all the soil from the bottom of the tool up through the tool. In the case of the right-hand image, it goes all the way up through the tool and ejects out to the side of the pile. In the case of different soil types, we'll look at different sort of enhancements for that airlift tool. So it could be high pressure jetting at the head, depending on what kind of soil you're trying to break up. In the case of clays, it typically then is lower pressure, higher volume water to kind of fluidize the clays, and then it's still airlifted up through the tool. But if you can imagine, the length of a jacket can get quite extreme depending on the water depth. So you imagine then the soil plug tool gets even longer because it has to go below mudline. So in the case of looking at larger jackets, we tried developing longer tooling, and it just becomes really challenging from a deck point of view, from a handling point of view. So what we looked at was looking at using the same technology, the same soil plug removal head, but instead of using a large tool, we actually used the pile. So you can see on the left-hand image, that's us with a deployment frame, lands out on pile top. There's a winch on the frame that drops the head down into the seabed, but inside the pile. We start the airlift process on the head, but we actually use the pile as a conduit. So you can see on the right-hand image, you can see just below where the red platform is, that's the water and soil from inside the pile coming up through the pile, hitting the bottom of our frame, and then getting displaced overboard. So then you've got access, you've removed the soil plug below mudline, you've got access to your cut location. So if you look back again at these skirt piles in the jacket, we would say these are battered piles, so they're at an angle. So both the skirt piles and the pin piles. So you can imagine then putting a cutting tool, such as these internal pile cutting tools, into there. Your cutting tool sitting at an angle, so it has to centralize within the pile and perform a cut and maintain the cut line. So some of the challenges we see with some tooling is that your cut maybe doesn't match up if you're not fully centralized within a battered pile. So we have seen evidence of that. So we had to look at our systems and perform cut. We essentially laid down piles with a cutting tool in it and just pushed the limits of where it would centralize, expanding the sort of arms on the centralizers into more of a ski model, so it had more power and more surface area to centralize. And then using the same cutting tool to cut anything from like a meter pile up to 1800 millimeter pile. So same system, just expanded out, so you can deploy one cutting tool and all you do is add spacers into it to allow you to centralize in larger piles. And then, so one thing we see is quite often is the request for castellated cuts. So we don't typically see the benefit of that compared to doing an angular cut. So this is a cut performed at 30 degrees. So the castellated cuts can be successful, you know, in air for topside removal. For doing it subsea below mudline becomes a lot more challenging than just performing a 30-degree cut. So it's a simpler option, but you've obviously then cut the steelwork at an angle so it can't move anywhere. So this is becoming more normal, a request for a below mudline cut than a castellated cut. If you don't have a castellated cut, basically it goes like that. So if you float away from a small vessel before the heavy lift comes, the castellated cut is, the idea is that nothing moves because it can't, because of the castellations. Same with an angled cut. The steelwork can't shift at all because it's cut at an angle rather than severed at level with seabed. So really, for us, it's looking at those applications where we've kind of taken standard cutting solutions. So looking at, well, what are the capabilities of Excalibur from a cutting perspective? What are our soil plug removal capabilities? Applications, so jackets started to get bigger. So okay, it's not then reasonable for us to scale up a longer tool to cut 100, 120 meters of a jacket. So then looking at, right, okay, how can we use the same application and just put a bit of thought into how we actually modify existing tooling to perform those type of operations. I would say we've been relatively successful, and it's become a kind of norm for jacket recovery below mudline is to go use abrasive systems and to go use soil plug removal tools such as ours. The next kind of step for us in looking at that type of jacket severance, so this is a solution looking at essentially pin piles, skirt piles, subsea infrastructure piles. So for the last few years, we've been working on developing underwater laser cutting. So this is to look at essentially being able to put a smaller deck footprint on your vessel. So again, perhaps even look at smaller vessels, being able to go and do the cutting application before the heavy lift comes in. Looking at ways to do things a bit cleaner and quicker. So a lot of the abrasive systems out there use either diesel-driven HPUs, diesel-driven pumps. This is a system you can plug straight into your vessel power. And the benefit of developing a new system. So a lot of our cutting solutions have some intelligence built into them, which I'll come on to, but this because it's a new system completely, we were able to develop it fully electronic and electric. So you get a lot more data out of the system than you maybe would out of some of the existing market tooling. So it really builds the kind of picture of the data set of what you can then build into, right, okay, what is a good cut? What is the tool telling us? What is the cut telling us? Start to build a data set of models for future sort of cut verification and AI sort of development. So it kind of starts to autonomize the whole system rather than being reliant on sort of interpreting what the system's telling you. This is a tool in development. So it's the first iteration, because we had pile cutting opportunities with Harbour Energy in the UK here. So the development was done in partnership with the University of Aberdeen and the Net Zero Technology Centre, and we had operator partnership, which for us was valuable. That was Harbour Energy. So their scope was to find us actual cutting solutions. So we knew the technology could work in a subsea environment because we'd done a previous phase of development. This was then going to look for actual cutting applications. So Harbour had a load of subsea piles to cut, so it allowed us to develop a pile cutting tool. And this is us during what we would call developing the tool to TRL8, so that is proven in a realistic environment offshore. This is us deploying it offshore a Biscalis vessel for Harbour Energy in the North Sea here, cutting, in this case, 24-inch piles, but the tool can obviously expand out to 30-inch piles, and then sort of validate the system in this environment for us to then make the case to then fully commercialize the model. So we're currently in the process of building a fully commercial model this year. So we're just at this to building the cost model around our third-party costs. So that is a full electronic PC-based control system, a offshore container with all that built into it, our own laser generator. So hopefully in the next few weeks, we're just starting to procure some of that equipment and look to build that up later in the year. But this existing system that we qualified to TRL8 lives and exists, so we are ready with this system. It's perhaps just not the full industrial version that we would call the TRL9 system. So yeah, we're beyond the developing the commercial model. What we're looking at is then building the capability. So similar to what we've done with Excalibur over the years, but maybe a shortcutted version rather than waiting, so pushing over 30 years. We're going to do this over the next year to push the boundaries of where we see this application working. So for us, that's water depth. So we've proven it TRL8 and 50-meter water depth. So it's the next step for us because we know there's pile and jacket cutting opportunities in deeper waters. So one of the benefits I've mentioned of developing a fully electronic system is that you get a lot of data for it. So for us, this kind of builds into the picture of cut verification. So a big thing for a heavy lift is, before you want to come in with that expensive asset, is to know that you've actually cut the jacket, or I mean, the top side is going to be a lot easier, but for below mudline cutting, it's really how do you know you've performed those cuts on all those piles so the heavy lift can come in and lift it, and it's only lifting the jacket weight plus a bit of seabed stiction. So for that, we've called this performance certainty. So it's really delivering certainty of performance. So it's building in a picture of cut verification system from all your system parameters. It's building in, can you get visuals on the cut, or can you laser scan a cut? And then as we start to build data sets of good cuts, then it's building that into an AI model to say, you know, fully autonomize that system to tell us, okay, we know for sure we've cut this because the data is telling us. You've got all the backup data if you want to see it, but you don't need to because the system actually tells us that. So it's really a kind of multi-phase approach. So we've been working in the last few years, again with lasers, but a slightly different application. This is laser scanning for cut verification. And then looking at instances where we have used laser scanning and there are challenges around that. So one instance we used it, we had really soft seabed. So the laser scan, what it does is it actually looks through the cut. So you can see the bottom middle image, that's a laser scan of a cut that we've performed. It's a wider cut because the client asked us to do this, what they called letterbox openings at the start and end of the cut, so we could see that it had overlapped. But in a case where you have soft seabed in there, it can actually wash back into the cut. So you can see in the top image there, is the sand is within the cut, but you know it's cut there because you get a visual before it washes back, and you can get a scan before it washes back. So it's kind of building into the approach. Okay, we have the scanner in there, we've got the visuals in there, which is a camera in the bottom right. We've got the process data, and then we've in the future got the AI model with the algorithm telling us what is a good cut. And it's really then building that into Excalibur systems. So then for us, it's looking into what we can take from a new system like the laser that we developed, an electronic control system, what of that we can enhance our existing Excalibur systems with, and then really build that data set up to start building the AI models around that. So you're going to start listening to the cut, you're going to start looking at what the data is telling you, and you're going to have robotic control, so all the on-tool sensoring telling you exactly what the tool is doing at any given time. So if you marry those and overlay those, you start to build up a real good data set of what can be built into an AI model. That's hopefully a reasonable summary of the operations for well cutting, for platforms, for topside removal, for jacket cutting solutions, and some of the kind of future developments around new technologies for cutting applications for jackets especially, and for some of the more intelligent ways of looking at how systems can start to really define what is a good cut, you know, what the data is telling us, rather than being more reliant on operators or kind of traffic light system of what we think the system's telling us, but it's not kind of got the data maybe behind it. And at that, I shall hand back to Rian, and I'm open for questions. Thank you very much.
Wonderful. Thank you so much, Craig, for your very interesting presentation on cutting solutions. I found that very insightful. We'll start with the Q&A, and I guess one of the advantages of hosting is that I get to start with the questions. So that's good. I'd like to understand a little bit more about your when you're doing abrasive cutting campaigns, how do you characterize and manage the fate of the spent abrasives, the cuttings, and the cement particles, or maybe the scale or any entrained hydrocarbons? Is it generally an expectation that you disperse to seabed, or is it recovery and containment where possible, or does it depend really on the well condition and the water depth?
Yeah, very good question. So in the case of, so you can be slightly different. If you've got hydrocarbons in your annulus, you're probably not in a position that you're going to be wanting to do the severance quite yet. So typically during if we're involved in environmental plugin, for example, we would be flushing out those annulus during the environmental plugin. So before you set the cement in an environmental plug, we perforate through to the annulus, flush out the annulus and the bore, so you have a clean environment at the environmental plug, so there's nothing above that. So that would deal with hydrocarbons. Regarding spent abrasives, typically that is just permitted off to leave on the seabed, and there may be traces of cement, but for the most part, we don't typically see cement at the top of the wellhead. I mean, there are cases that I've shown there that there is cement in the wellhead, the well bore at that point, but a lot of the cases the cement's actually slumped down below the cut line. But again, that would all be permitted to leave in sight. You wouldn't want to be trying to go and clean up abrasive material. It's typically garnet, so it's either mineralized rock, crushed rock, or sand. So it's a natural product anyway.
Yep. Okay, great. Thank you. We have a question. When cutting the angled skirt piles with the internal cutting tool, you said you were getting misaligned cuts and tried different approaches. How often were you getting these misalignments and how bad were they? Have you reduced the occurrence and by how much?
That's a good question. When I say I've seen misaligned cuts, they weren't our cuts. I've seen pictures of cuts that perhaps show that other people have had the same challenge of cutting a battered pile. We witnessed that during trials onshore, so we knew that. So the previous version of the cutting tools I showed had single arms coming out, so it was like this rather than a ski that came out like this. We had single arms, so you'd only had 3 points of contact at the top of the tool and 3 at the bottom, and there just wasn't strength to maintain that. So you imagine the tool's off just even slightly, and then the cutting head's pointing at a funny angle. So we found that onshore, we developed the ski solution and strengthened up the centralizer. So we haven't really seen that ourselves, but I know it does occur.
Yeah. Okay, thank you. Please don't be shy. Put your questions in the chat and I'll read them out. I'll go with another one of my questions. For the Australian style approvals, the operator needs to demonstrate impacts and risks are acceptable and reduced to a lark. What evidence package do you typically provide to support that? Do you use discharge volumes or plume assumptions or cut verifications, noise, anything?
We can support on all of those. It depends what the application is. So if it was environmental plugin, for example, all the wellbore fluid that we deal with, so whether it's the wellbore or the annulus, all comes back to vessel. And we don't discharge any of that into the seabed. So it all comes back and either can be cleaned up on the vessel for clean water discharge, and then you've got a small volume, or you can take the whole lot back on shore. Same for cement. We only pump cement that lids in the wellbore after we leave for the environmental plugin. For severance, we obviously offer all the data on the garnet we're using, so that can be permitted in to be left on the seabed. But again, it's not a huge volume of garnet. It's not like when we're talking about water abrasive garnet, it's not a huge mix of actual garnet quantity within the cut. So again, yeah, all permitted through the vessel company typically.
Yep. Okay. So if I'm needing to cut, when should an operator choose abrasive cutting over diamond wire, mechanical cutting, shears, or other severance methods? What are the decision drivers? Is it the configuration of the casing? Is it the depth below the mud line? The amount of marine growth, environmental controls? I mean, what's the decision making that goes on when you're trying to decide how to do your cutting?
Yeah, it's a good question. I can understand that would be a challenge for operators to decide that. I mean, typically, if you're going to cut below mudline and you've got access internally, for me, I wouldn't promote dredging and severing from the external, no matter what kind of cutting tool you want to use, whether it's abrasives externally or a diamond wire, because the volume of seabed disturbance. Because you imagine the jacket I showed you with the skirt piles and the jacket legs, you can imagine the amount of seabed you'd have to move to get 3 meters below mudline to cut those externally. So for me, that's not a reasonable option if you've got access internally. And typically internally is going to be abrasives because we don't see knives of the size to do pile cutting. So typically it's abrasives that are used for pile cutting, for internal cutting below mudline. For wells, again, specifically in some of the more challenging wells, I think abrasives are better suited. So if you take the triple bore, for example, going into one bore and cutting all the way out through 3 bores plus the outer conductor, there's not a set of knives suited to do that. I don't believe that if you try to do that with explosives, you'd need such a volume of charge. It would be so disruptive. So I don't think that's a reasonable option, and you'd probably need to go in and set off separate charges to get through the whole lot. So certainly for those applications, I think abrasives, and for well severance generally, the good thing about abrasives is you go in with one tool and you cut the whole lot in one go. With knives, for example, you might go in and cut a couple of inner conductors, pull those in, go in with a larger set of knives to do the outer. So that has benefits. And every technology has benefits. It's just looking at the right one for that application, and we're not shy of saying if we think something's too risky for us, we would welcome a chat with a client on what their challenges are and have a very frank and open discussion around those.
Yeah, communication is always key, isn't it, Craig? Well, there are no further questions, so I am going to finish it here. Thank you everyone for joining us at today's webinar. Please stay tuned for upcoming webinars where we discuss all about decommissioning. So thank you everyone and good afternoon.